Welcome to a short presentation on the principle of mathematical induction. Now that is not actually in this course, but what is in the course is the process of mathematical induction, which is an abbreviation of this one. But students often ask me, what is the real thing? And this is the more rigorous proof of propositions using the principle of mathematical induction. Let's have a look at it, and I think what does induction mean for a start is the first word we should look at. And I think looking around the screen you can see the idea that when you use many actual examples and come to some conjecture, this process is called inductive reasoning. Come down the bottom here. You're going to make up a conjecture based on actual examples, and then maybe formally make it a formal statement mathematically there. So that's the idea. Come over on this side. We're finding another series type situation where we see a pattern, a half, 2/3, etc., as we add that second fraction, which is the original second integer there times the next one. We're seeing a pattern there. So we're saying that is going to be the sum, n over n plus 1, if we look at that increasing sequence there. All right, so that's the idea of inductive reasoning. We're going to take examples and make some conjecture. But of course, deductive reasoning, just coming down here a bit, is we're saying, well, can we get a proof of that conjecture? And that involves deductive reasoning, where we don't base the whole thing on examples. So the principle of mathematical induction is a deductive proof based on starting with an example and then having an inductive step where we prove something will be true if others are true. Let's have a look at that process. And I want to take you through it fairly informally for a start. And here it is. Screen clippings are from Hayes and Harris Publications, the higher level International Baccalaureate textbook they brought out there. So I'm going to take this one here, what we just saw at the top, the sum of consecutive odd integers. So we generate an odd by putting I equals 1 through n in there. Just check it here. 2 times 1 is 2, take 1 is the first integer. 2 times 2, take 1 is the next integer. Okay, so do you agree this is the sum of the first n odd integers, as we saw up before on that first window? And we're saying the sum is equal to n squared. And we're going to say for all n member of the positive set of integers. Okay, so what we need to do in this process, and let's just follow it through now, we want to have a starting point. So let's start with the first positive integer, n is 1. So the sum here, I equals 1 to n, of 2i take 1, the left-hand side, you can just put left-hand side equals if you want to, is 1. It's just the first one itself. And then n squared is 1 squared would equals 1. Therefore, true, the proposition is true for n equals 1. So we've established that it is true for a starting value right at the beginning of the set of integers. Now, this is a strange step. Assume true for case n equals k. So case n equals k, the proposition in k, is that the sum I equals 1 to k of the integers up to there, 2k take 1, equals k squared. Okay, so what does that mean? So the proposition in k is that what does that mean? It's 1 plus 2 plus 3 right up to the kth odd, which is of the form k take 1, and all of those will come to k squared. So we're going to assume that. You say, gee, honey, that's supposed to be a proof, isn't it? Well, let's go down and see what we're going to do and see if you can understand it. Now we're going to prove it true, assuming this for case n equals k plus 1. So the proposition k plus 1 is that 1 plus 2 plus 3 up to, now the proposition k plus 1 will be 2k plus 1, take 1. It will be the next term on. Okay, and the term in here, I'll just show you, the term before the next one, or the k plus 1, will be the kth term, won't it? The proposition in k plus 1 will involve one more odd integer added on. Okay, and here the whole term is 2 times that integer, take 1. That's the k plus 1th odd term. All right, so let's have a look here. We're going to say that's the proposition. So let's consider the left-hand side. You could just put left-hand side equals. So I'm going to write it out here again. 2k take 1 plus the extra k plus 1th odd on the end. Now consider that it equals, now what's this much here? This is our assumed proposition in k. So we're going to say we assume that, so it's k squared plus 2 lots of k plus 1 take 1. Just come down here a little bit. Okay, so this is then k squared plus 2k, expanding this bracket, plus 2 take 1, which is equal to k squared plus 2k plus 1. Okay, let's keep going. We'll have to go across here now because I've cramped myself up. So this is equal to k plus 1 squared. Wow, we just did it. Okay, and oh, we come up here. I've made a mistake already, haven't I? Up here, this was supposed to be k plus 1 squared, wasn't it? For the proposition in k plus 1. So therefore, it's true for proposition in k plus 1, that is, n equals k plus 1. Now, what have we just done? Have a look at the dominoes. Got a clue? What have we done? Well, we've pushed the first one over, and that's that line. It's true for the first example. And then this line, which is called the inductive step, says what? It says if we assume it's true, then the next one will be true. That's like saying, hey, if you push that domino, we've just shown with this step that if one falls, the next one, the next one, the next one, the next one will fall. This inductive step is showing that, isn't it? It's showing that once one falls over, and we've said assuming one falls over, then the next one falls over. Okay, in strict mathematical proof. Sorry about this down here. I hope you picked that up, that the proposition k plus 1 has to come to k plus 1 squared. Do you get the idea? Now, I've done it in a very broken down way. We usually try and put it together a bit more formally than that and end up with a formal statement at the end. Let's have a look at the example now. So come down here. So here's the proposition. Here's the principle of mathematical induction, usually PMI, principle of mathematical induction. So if Pn, a proposition, is a proposition which is defined for all integers, needn't be all positive integers, could be from A, and A is an integer. You try to prove the starting one is true, excuse me, and then you've got to prove that P of k plus 1 is true whenever P of k is true. That's the inductive step. And then P of n is true for all n greater than or equal to A. Okay, so we assume P of k and then go on and prove P of k plus 1, which is what I just did up there. So let's have a look at it more formally structured. I wanted to take you through those steps and associate them with the domino principle. Okay, you must show that the first one falls. You must show also that once one falls, the next one falls. That's the inductive step here, that if one falls, the next one falls. P of k plus 1 is true whenever P of k is true. So we actually assume that and show that the domino effect is going to cause eventually all of them to fall. All right, so come down and let's have a look at some examples. So here's an example from Hayes and Harris. prove that 4 to the n plus 2 is divisible by 3 for all integers z. Okay, starting at greater than or equal to not negative ones. So starting at greater or equal to 0. And you could use the binomial. So they're giving you a hint there. Or you could use the principle of mathematical induction. So let's look at the setting out of those two. So if n is 0, go back up here. 4 to the n plus 2 is 4 to the 0 plus 2, which is 3, which is divisible by 3. So I like to put case n equals 0 there. You can please yourself there. Now let's use the idea that 4 is 1 plus 3 to the n. And with a binomial expansion, it's the first term to the nth with no 3. Then it's Cn1, 1 to the n take 1 and 3 to the 1. Then it's Cn2, 1 to the n take 2 and 3 to the 2. The 1s don't appear in here because 1 to any power is 1. So you put all those terms down and you've still got the plus 2 on the end. Now, if you add the 1 and the 2, you get 3. And then all of these others have obviously got powers of 3 in them. So you take that out as a common factor and then reduce the powers of 3 in here, factorise it. Now, the important thing is to notice that this big bracket around all these is an integer because all the combination coefficients in here, you remember Pascal's triangle and all that stuff, are whole numbers. So therefore it's 3 times by one big integer there. Therefore 4 to the n plus 2 is divisible by 3. A nice neat little proof there. Got nothing to do with what we're talking about here, however, because this is what we want to do. We want to do it by the principle of mathematical induction. So there you state your proposition. So I want you to follow this format. So proof by, and put it by the principle of mathematical induction, or by PMI. If n equals 0, so that was the starting value, back at the beginning proposition it said, here it is here, you must start with whatever that says. N equals 0, show the left hand side as we did before, it's true, therefore P of 0 is true. Now, I like to put here assume P of k is true, then you put this down. 4 to the k plus 2 must be 3 times some integer, and a is bigger than or equal to 1. Now, I like to consider the proposition in k plus 1. And then you start with that. Start with left hand side, break it down, try to work in the previous proposition. You must relate P of k plus 1, the inductive step this is, back to your allowed assumption, which is proposition k. Relate it back to that, okay, because you've got to work that in. So 4 to the k plus 1 is 4 to the 1 by 4 to the k, which is 4 to the, and we're allowed to use it using the proposition in k. This is the inductive step here. Plus 2, so 12a take 8 plus 2, 12a take 6, and 12a is here. We can factorise this, take 3 out, 12a becomes 4a, take 2. Now 4a take 2 will be an integer, because a is an integer. So in other words, you've been able to show that proposition k plus 1 consists of an integer times 3, which is the definition of divisible by 3, as long as 4 to the k plus 2 is divisible by 2. So what you've got to do now is make this statement, that therefore the proposition in k plus 1 is true. So here summarising it, since P of 0 is true, P of k plus 1 is true whenever P of k is true. That's the inductive step. So you must end up with this formal statement. Then Pn is true for all n greater than 0 if n is an integer, and by the principle of mathematical induction. So this final line is what I didn't do up there, just showing you the idea. So that must be a summary at the end. So you must say you start off with a particular value. This might be 1, 2, 3, whatever, and then make the statement you've shown that P of k plus 1 is true whenever P of k is true. That's the inductive step, and therefore it's true for all integers greater than or equal to 0. Right, time for you to practice. So try to copy that sort of process, and I don't want you to just to be a monkey copying other monkeys, but the idea is you do need to have the formal structure here. So you can't make up your own structure. This is more formal than what's in this course, where we use the process of mathematical induction, which is a short version of this really, not quite as rigorous. All right, okay, try these and see what you think. Let's go on to another example. One with sequences and series again. So let's say we're summing i's from 1 to n, and they are the positive integers, the sum of all the positive squares of all the positive integers. So I is a positive integer, and we're going to sum n of the squares of them. Okay, and we're supposed to get this formula, and then find there the sum of the first 100 integers squares of the integers. So you state the proposition, okay, for n as a member of z plus. So automatically, and now putting the proof, I would say case n equals 1. I like that better. Why is it n equals 1? Because it's a set of all positive integers would start at 1. So you can do this. Left-hand side equals 1 squared is 1. Right-hand side, you can do that. Therefore, P of 1 is true. Now, if P of k is true, so I like to put, as I told you before, assume P of k is true, and then you write that down, P of k. So you're going to assume this line. This is the inductive step now. What you want to say, this is saying if a domino falls, and we've got the first one, n equals 1, if a domino falls, we're going to show that the next one must. Okay, that's the idea, the next one must. So let's consider the proposition. Now, I don't like thus, I prefer to say consider P of k plus 1. And that's this. Okay, that's P of k to there, and you've got k plus 1 will be the next integer squared. So I'd like to put here not thus, but consider P of k plus 1. Consider P of k plus 1. And that's this one. So it's just left-hand side, and we're saying we're going to consider what that comes to. So here's the crucial line. It's showing you P of k plus 1 is P of k with k plus 1 squared on the end. So you can put in the formula using P of k. You should put that. This is a very important line, this inductive step, because you must make a connection, connect to P of k so you can work it in. That's what you're trying to do. So here we are. We've got that connection, and now the trick here is to get all over common denominator. So multiplying this little term by 6 over 6, you've got that extra term over the common denominator. And then if you try to factorise it, because just remember what you're trying to do, you're trying to get this sort of form with k plus 1s in there. Okay, so let's factorise it, take out k plus 1, and then we've got this thing here with k plus 1 in it, and expanding that, and then factorising that, and you're trying to get the form here, aren't you? K plus 1 here by k plus 1 plus 1 lot of 2k plus 1 plus 1. Okay, can you see that pattern? Because when you do this, this is the proposition in k, that's the top line, then it's got to become k plus 1 in here, k plus 1 by k plus 2 by 2k plus 1 plus 1. So that's what they're doing here. Okay, there's k plus 1 plus 1 and 2k plus 1 plus 1. So they are the terms that these become if you put k plus 1 in there. It's k plus 1 plus 1. This is 2k plus 1 plus 1. So that's showing the proposition in k is true. So now you make a statement. Since P of 1 is true and P of k plus 1 is true whenever P of k is true, inductive step, then P of n is true for all n, which is a positive integer, by the principle of mathematical induction. Okay, so because it's a formal proof, this formal statement should be present, all parts of it. So it's showing you two things. I've proven it true for a starting value, and then I've proven it with the inductive step that if this domino falls over, this one will. Okay, got the idea. Now we can use it to find the sum of the squares of the first 100 integers, which would be up to there, and it's that big number there. Okay, so we're just going to put 100 in our formula and divide by 6 there. Do you get the idea? It's not too bad, is it? A little bit more strict and formal than the method of mathematical induction that's in this particular course. We call it the process of mathematical induction. Okay, so come down and here's some for you and see what you think. There it is, 9b2, and have a go at that. And this is a series ones. I think you're seeing now the important idea is connect the proposition k plus 1, and this is the inductive step, the domino principle, the proposition in k, and then you can work in your P of k result and build from there. That's the idea. All right, well, I hope you've enjoyed that. This is not part of the course, but you are allowed to use it if you want to, instead of the process of mathematical induction, because it is a stricter form. So you can choose what you want to when you have tests or proofs of this type. You can use the principle of mathematical induction now. So good luck with that. Cheers for now.